Hello viewers, in this video I am going to explain about the specific speed of a turbine. Let us first see what do you mean by a specific speed. Specific speed of a turbine is defined as the speed of a geometrically similar turbine which produces a unit power when working under a unit head. By geometrically similar means that turbine is identical in shape, dimension, blade angles, gate openings, etc. Let us now see some of the pictures of turbines. This is a Pelton turbine and the second is the Francis turbine. Now let us see the derivation of specific speed. For this, we'll consider a series of geometrically similar turbines. The derivation starts with the power equation P equal to WQH, where W is the specific weight, Q is the rate of flow, and H is the head of the turbine. Hence, the P is proportional to QH. For Francis turbine, Q is pi dB VF, so P becomes proportional to pi dP Vf into H. So this Vf can be replaced as under root 2 GH. So we'll say Vf is proportional to root H. Hence P is proportional to dP under root H into H. This becomes equation 3. Further, the peripheral velocity is given by V equal to pi dN by 60. So here V becomes proportional to dN. So from equation 2 and equation 4, we can write dN is proportional to root H. If n is taken on the right hand side, it becomes d is proportional to root h by n. Further, b is proportional to d when all the turbines are geometrically similar. Therefore, b is proportional to root h by n. So the equation 3 we have just now seen is P proportional to dB root h into h. Here I'll replace d and b from equation 5 and 6. So that becomes P is proportional to root h by n into root h by n into root h into h. So root h into h becomes h to the power 5 by 2. N becomes n square. N into n becomes n square. So that gives it as n square as proportional to h to the power 5 by 2 by p. So therefore, if I take the square root of both the sides, I get n is proportional to h to the power 5 by 4 by root p. N is equal to c h to the power 5 by 4 by root p, where c is the constant of proportionality. So we know for 1 meter head, the power developed is 1 kilowatt and the speed is specific speed. So n is equal to ns. Hence, I'll replace n as ns, c as it is, h is 1, p is 1. So we get c equal to ns. Therefore, finally equation 7 gives n equal to ns into h to the power 5 by 4 by root p. But we want the equation for ns, so that's why we can write ns equal to n into root p upon h to the power 5 by 4. Here the units are for n and ns. These are given in RPM, P is in kilowatts, and H is in meters. So this is the equation for specific speed of the turbine. The various types of turbines are there depending upon the specific speed ranges. So when the range of the specific speed is less than 30 rpm, it is a single jet Pelton wheel. When the range of specific speed is between 30 to 50 rpm, it becomes a multiple jet Pelton wheel. When the range of specific speed is between 50 to 260 rpm, it is a Francis turbine. And for 260 to 860 rpm specific speed, it is a Kaplan turbine. So, based on what is the specific speed, here in this numerical, we are going to find out what is the type of turbine. So, the given data is a hydraulic turbine working under a head of 180 meter runs at 325 rpm and the discharge being 0.71 cubic. The overall efficiency of the turbine is 84%. What is the type of turbine? To find out the type of turbine, we must first find out what is its specific speed. So let us begin. So H is 180 meters, N is 325 meters, RPM, Q is 0.71 cubic, and neta 0, that is efficiency 84%. So let us first find out the power developed by the turbine, which is P equal to neta 0 WQH by 1000. The answer will be in kilowatts. So this comes out to be 1053 kilowatts. Now the specific speed as we have derived is given by Ns equal to n root P by h to the power 5 by 4. So that comes out to be 16 rpm. This is less than 30 rpm, hence this is a single jet Pelton turbine. So viewers, in this numerical, what is given is the head of the turbine, the speed of the turbine, the discharge of the turbine, and the overall efficiency. By using this data, we can find out what is the type of turbine. So idea is clear. We'll solve another numerical. So here the head is given as 25 meters, the speed is 200 rpm, the discharge is 9 cubics, and the efficiency is 90%. So the procedure remains same. First we have to find out what is the power generated. So power generated is neta 0 WQH by 1000, where neta 0 is 0.9, W is 9810, Q is 9, H is 25 divided by 1000. That comes out to be 1986.5 kilowatts. So the specific speed is then found out as n root P by h to the power 5 by 4. By substituting all the values, we get the specific speed as 159.5 rpm. Now from the table if we check, this is between 50 to 260 and hence the type of turbine is Francis turbine. So friends, with this data we can find out the type of turbine. So this is about the specific speed of a turbine. Now the performance of the turbine under unit head. So now under 1 meter head we can find out what is the speed of the turbine, what is the discharge of the turbine, and what is the power of the turbine. Under 1 meter head, these are called as unit speed, unit discharge, and unit power. If for a given turbine under the heads of H1, H2, H3, the corresponding speeds are N1, N2, N3 and the corresponding discharges are Q1, Q2, Q3, the power developed are P1, P2, P3, then we can define unit speed as Nu equal to N1 by root H1, N2 by root H2 and N3 by root H3. Unit discharge can be defined as Qu, which is equal to Q1 upon root H1 equal to Q2 upon root H2 equal to Q3 upon root H3. Similarly, the unit power is written as Pu equal to P1 upon H1 to the power 3 by 2, P2 upon H2 to the power 3 by 2 and P3 upon H3 to the power 3 by 2. Thus, if speed, discharge and power developed by the turbine under a certain head are known, the corresponding quantities for any other head can be determined. So let us find a derivation for this. The unit speed is found out by the expression V equal to pi dn by 60. So here V is proportional to n. Also we know V is equal to under root 2gh. So we can say V is proportional to root h. So n becomes proportional to root h. Proportionality is replaced into equality and we can add one constant of proportionality as Nu. So that becomes n equal to Nu into root h, where when h is equal to 1, n becomes Nu. So Nu represents the speed of the turbine under unit head and Nu is the unit speed of the turbine. The expression is Nu is n upon root h. Now the unit discharge. What is unit discharge? Here we can find out the discharge Q as area of flow into velocity of flow. But for a turbine, the area of flow is a constant and hence Q is proportional to Vf, which is proportional to root h. So that becomes Q is equal to K2 into root h. So for h is equal to 1 meter, Q becomes Qu and hence K2 becomes Qu. So we get the expression as Qu equal to Q upon root h. So this is the performance of the turbine in terms of discharge. Similarly, the performance of the turbine for 1 meter head, that is unit power. So the power developed by the turbine working under the head say 1 meter is known as unit power of the turbine. So we know P is equal to WQH where V is under root of 2GH. So we can write it as P is equal to WQH. So that becomes K2 into H to the power 3 by 2. So if H is equal to 1 then P becomes Pu. So Pu equal to K2 into 1 to the power 3 by 2, that becomes K2. So becomes P equal to Pu into H to the power 3 by 2, resulting in the expression of Pu, that is unit power, as P upon H to the power 3 by 2. So this is how the unit power is derived, which is the performance of the turbine in terms of the power. Now let us solve an example to find out the unit speed, unit discharge and unit power. In this numerical, the working of the turbine for 25 meter head is known and we have to find out the performance of this turbine under the head of 20 meter. So that means the H is given as 25. We have to find out for H1 as 20 meters. So performance of the turbine under the head of 20 meters. So we have to find out the performance under 20 meters. Using the expression of unit speed, we know nu equal to n upon root h equal to n1 upon root h1. So it is 200 upon root 25 equal to n1 upon root 20. So that gives it as n1 as 178.9 rpm. Similarly, if you find out Qu, that is Q upon root h equal to Q1 upon root h1, we get 9 upon root 25 equal to Q1 upon root 20. That gives it Q1 equal to 8.05 Qm. So this is the unit, this is the discharge under the head of 20 meters. Now, unit power is Pu is P upon h to the power 3 by 2, which is equal to P1 upon h1 to the power 3 by 2. So power we had calculated as 1986.5. That's the same as in numerical 2. Divide by 25 to the power 3 by 2, which is equal to P1 upon 20 to the power 3 by 2. By this, we find out the power as 1421 kilowatts. So viewers, the performance of any turbine can be understood if we know the performance of that turbine under the some head. So we can know its performance for another head. Thank you for watching.